4.8, number 373. We have the limit as x approaches 0 of 1 plus x to the nth power minus 1 over x. There's a couple ways to solve this problem. We will use L'Hopital's rule firstly, and maybe I'll show a second way. So first of all, let's make sure L'Hopital's rule applies. X approaching 0 would imply that the numerator here, this term, the numerator is heading towards 1 plus 0, heading towards 1. 1 to any power would be 1. 1 minus 1 would be 0. The top's certainly heading towards 0. The bottom, all the more so, obviously. Since x is heading towards 0, x is heading towards 0. All right, so we have the indeterminate quotient that we're looking for to use L'Hopital's rule. So let's go ahead and use it. So the limit of 1 plus or 1 minus? Not 1 plus. 1 plus x to the nth minus 1 over x as x approaches 0 should be the same as the limit of the quotient of the derivatives through L'Hopital's rule. So the quotient of derivatives, the derivative of x is 1. The derivative of 1 plus x to the n minus 1 will be, well, the minus 1 is going to just vanish when you use the derivative on it. And 1 plus x to the n is a power rule. So the n will come down because it's a constant. So n, 1 plus x to the 1 power less. And normally I would multiply by the derivative of the inner function, but that's going to be 1 in this case. So when I complete the chain rule, all I would do is multiply by 1, and that will do nothing, so I'm not going to write it. All right, now as x goes to 0, there's no longer a 0 of 0 case. We have a defined limit here. So if x is heading towards 0, then we'll get n 1 to the n minus 1. But 1 to any power, like I just said, is 1 back again. So we get n times 1 is n. Okay, so there's our answer. All right, there's another way to look at the problem, though. We don't have to use L'Hopital's rule to find the answer. We can view the limit as x approaches 0, 1 plus x to the n minus 1 over x. Perhaps there's a way to view it, the whole thing, as a derivative. All right? If we just write out the definition of derivative we've had before, using some of the features here, right? Limit as h approaches 0 of a function, and usually you have a plus h in here, right? Minus f of a all over h. Okay? So we usually use h for the symbol in here, but it looks like they've taken h and used x. If I replace h over here with x, which I'll do right now, I'll just erase these to make the comparison perhaps more obvious between these two. Again, what is this thing? This is nothing other than f prime at a, right? This is a definition of f prime at a. So if I replace this with x, it looks a lot more like this setup here. So x in the bottom, limit as x heads towards 0, limit as x heads towards 0. I've got a function, I've got some kind of function here happening to a plus x. Well, what's the function? It looks like it's the nth power function. The nth power function is f, and a is apparently 1. Right? If that's the case, if f of x is x to the n, the nth power function, then I would expect that f of a, right? Let me write one more thing here. If our supposition is correct, f is the nth power function, and a is 1 from this setup on the left here, right? The left part of the numerator, makes that pretty convincing. Then it should be the case that f of a will be 1 itself, that the right-hand side of the numerator should be the same as the right-hand side over here. So f of 1 equals 1 to the n, right? F of x is x to the n, I plug 1 in, I should get 1 back out, and I do, right? 1 to the power is 1. So therefore, that means that this limit that we started with is nothing other than the definition of derivative for some function. The function happens to be x to the nth power. At some location, the location is 1, right, as we saw here. So therefore, if I just take the nth power of x, right, so f prime of x is nx to the n minus 1, similar to the move we used up here when taking the derivative of the numerator for L'Hopital's rule. But here this is independent of L'Hopital's rule. This is just comparison with the derivative structure for a function. So we have f prime is nx to the n minus 1, and therefore f prime at a, which is the same as this derivative by definition, which is the same as this limit by comparison. So it implies that f prime of a is the same as f prime of 1, but f prime of 1 is n1 to the n minus 1, because we said f prime was nx to the n minus 1. And so therefore we get n like above. There'd be two basic ways to take care of this limit.